Okay, so today we shall discuss a little bit about cylindrical waveguides and cylindrical cavity resonators, and then we shall see how what happens when an atom placed within a waveguide, a cylindrical waveguide or within a rectangular waveguide interacts with the radiation, how it induces transitions of the electrons from one state to the other, and by measuring these transition probabilities which can be estimated by measuring the relative population of the electrons in the higher states relative to the lower states, and relative population of the electrons in the excited states relative to the lower energy states. You are able to estimate the dimensions of the waveguide on a nanoscale and so on. So, the first problem here is that you have a cylindrical waveguide like this. It extends along the z axis, its axis is parallel to the z axis and its radius is r. So, the outer boundary, it has got only an outer boundary r equal to r or rho equal to r, where rho is root of x square plus y square, the distance of a point from the axis, from the z axis, and rho equal to r is a cylindrical boundary, and it is a perfect conductor. Boundary r equal to r or rho equal to r is a perfectly conducting surface, perfectly conducting boundary. So, if you apply the boundary conditions, that the tangential component of the electric field vanishes on this boundary. Ez is the tangential component and E phi is another tangential component, E phi, where rho phi z forms the cylindrical system of coordinates. Rho equals square root of x square plus y square, phi equals tan inverse of y by x, and z is of course z itself. So, this is the x axis, this is the y axis, and this is the z axis, and this angle is phi. So, if this is x y z, this angle is the angle made by the plane parallel to the z axis and passing through the given point, that is, which contains the z axis and passes through the point x y z. The angle made by that plane with the xz plane is phi, and the distance from the axis, the distance of the point from the axis is rho, which is square root of x square plus y square. So, the boundary condition is that the z component vanishes and the tangential component E phi at rho equal to r, that also vanishes, and the normal component of the magnetic field, since B is mu h, Bn should vanish. That means h rho at rho equal to r, that should vanish. The normal component of the magnetic field should vanish on the boundary, and it extends along the z axis. This is a cylindrical waveguide, and when you cover the top surface with a conductor and the bottom surface also with a perfect conductor, you get a cylindrical cavity resonator antenna. You get a cylindrical cavity resonator antenna, so that you have a surface current density on all the surfaces which radiate out into space, and you can calculate in principle the radiated field pattern, the Poynting vector, and so on. So, let us see how to analyze it. Last time we had seen that if we write the electric field and magnetic field, suppose they have the dependence on z as e power minus gamma z, that means you can write E as E of x y z can be written as some E of rho phi e power minus gamma z. Likewise, h of x y z can be written as h of rho phi e power minus gamma z. You see, rho phi is the plane polar coordinate of the point. It is an alternate parametrization of x1y of the plane of the point in the xy plane. So, it is related, either you parameterize the xy coordinates of the point by rho or phi polar coordinates, plane polar coordinates, or by x and y. So, x is obviously equal to rho cos phi and y is rho sin phi, or equivalently you can go back from rho and phi to xy, from xy to rho phi. Rho equals square root of x square plus y square, and phi equals tan inverse y by x. So, we have seen that when you have a exponential dependence upon z as e power minus gamma z, where gamma is the propagation constant, then you can write the transverse component of the electric field, transverse component as E rho into rho cap plus E phi into phi cap. Rho cap, phi cap are the unit vectors along the rho direction and along the phi direction. It is also the same as of course Ex x cap plus Ey y cap, and you can write this as minus gamma by h square del perpendicular Ez minus j omega mu by h square del perpendicular hz cross z cap, and similarly E h perpendicular you can write as minus gamma by h square by duality del perpendicular hz plus j omega epsilon by h square del perpendicular Ez cross z cap. Or equivalently, using the fact that the gradient operator in the plane polar coordinate system can be written as, in the Cartesian coordinate system it is x hat dou by dou x plus y hat dou by dou y. If you use the change of variables, right, for example you write x hat, you write the derivative with respect to x as dou rho by dou x dou by dou rho plus dou rho by dou y dou phi by dou x dou by dou phi, and similarly dou by dou y you write as dou rho by dou y dou by dou rho plus dou phi by dou y dou by dou phi, and use the fact that del rho divided by mod del rho is rho cap, and del phi divided by mod del phi is phi cap. The unit vectors along the rho cap and y along the radial direction rho cap and phi cap direction. That is, if you take the system of coordinates to be like this, then this is rho cap. Here all at this point this is rho cap. Rho cap changes from point to point and phi cap is perpendicular to it. Here phi cap is perpendicular to it. So it is an orthogonal coordinate system. Rho cap, phi cap, z cap. Rho cap, phi cap, z cap are mutually perpendicular unit vectors. At each point they define a frame, a local Cartesian frame at each point in space. Then you can write down del perpendicular as, del perpendicular can be written as rho cap dou by dou rho plus phi cap by rho dou by dou phi. And if you substitute that into the previous equations, you get from E perpendicular is equal to minus gamma by h square del perpendicular Ez minus j omega mu by h square del perpendicular hz cross z cap. If you separate out this into components, you get E rho equals minus gamma by h square dou Ez by dou rho minus j omega mu by h square. So dou hz by dou phi into phi cap cross z cap by rho. So del perpendicular hz is the phi component is 1 by rho dou hz by dou phi, and phi cross z cap is minus rho cap, right. You use the fact that rho cap, phi cap, z cap form a right handed coordinate system at each point, so that rho cap cross phi cap is equal to z cap, phi cap cross z cap is equal to rho cap, and z cap cross rho cap is equal to phi cap. So if you take phi cap cross z cap, you will get rho cap. So it will be there will be a minus sign. Del perpendicular, for example, if you want to write down del perpendicular hz cross z cap, del perpendicular hz cross z cap is equal to dou hz by dou rho into rho cap plus 1 by rho dou hz by dou phi into phi cap. And you are taking the cross product of this with z cap. So the rho cap contribution will come from this term, phi cap cross z cap is equal to rho cap. Similarly, you get E phi as minus gamma by h square dou Ez by dou phi. You put a rho here plus j omega mu by h square. Rho cap cross z cap is phi cap. So rho cap cross z cap is minus phi cap. So it will be dou hz by dou rho. Right. So when you apply the boundary condition that Ez vanishes on the boundary surface, you also have to apply the condition that E phi will vanish on the boundary surface, because E phi is also a tangential component to the boundary. But hz anyway hz does not vanish, Ez vanishes on the surface. So dou Ez by dou phi will automatically vanish. So you have to Since Ez vanishes on the surface rho equal to r, dou Ez by dou phi will also vanish. So it is equivalent to saying that dou Hz by dou rho should vanish, or equivalently the normal derivative of Hz should vanish on the surface. So the boundary conditions can be translated as Ez is equal to 0 when rho equal to r, dou Hz by dou rho equal to 0 when rho equals r. Right, these are the two boundary conditions which should be satisfied. And we solve the Maxwell equations. We solve the third component of the Maxwell equation, namely del perpendicular cross E perpendicular is equal to minus j omega mu Hz into z cap, and del perpendicular cross H perpendicular is equal to j omega epsilon Ez into z cap. These two equations will give you the Helmholtz equation, namely del perpendicular square plus H square acting on Ez Hz is equal to 0 within the boundary, that means for r rho lying between r and 0. And the only difference with the rectangular waveguide situation here is that the two Ez and Hz are satisfying the Helmholtz equation, but with different boundary conditions, namely Ez at rho equal to r is 0, that is Ez satisfies the Dirichlet boundary condition, whereas Hz satisfies the Neumann boundary condition as we just saw for the normal component of the magnetic field to be 0. So you get different eigenvalues in this place for modal eigenvalues for when you choose transverse electric and transverse magnetic. Transverse electric means Hz is not 0 but Ez is 0, then you have to apply the Neumann condition, and transverse magnetic means Hz is 0 and Ez is not 0, so you have to apply the Dirichlet boundary conditions. So if you solve this equation, for example using the separation of variables method acting on psi rho and phi is 0, that psi can be either Ez or Hz, then what you get is that you express the Laplacian, two-dimensional planar Laplacian in plane polar coordinates, 1 by rho dou by dou rho rho dou by dou rho plus 1 by rho square dou square by dou phi square plus H square acting on psi is 0. So you write psi, separate the variables out, psi rho phi is r of rho multiplied by phi of phi. If you separate it and substitute this into this equation, what do you get? You get dou square by dou rho square plus 1 by rho dou by dou rho plus 1 by rho square dou square by dou phi square plus H square acting on psi is 0. So if you substitute the product form, you get r double dash of rho by r rho. If you separate out the variables and substitute for psi rho phi r rho into phi phi plus 1 by rho, remember you are substituting psi rho phi equals r of rho multiplied by phi of phi. So plus 1 by rho r dash of rho by r rho plus phi double dash of phi by rho square phi phi. You substitute it and divide by the product r rho phi phi. So phi phi plus H square equal to 0. Multiply everything by H rho square, here also you have rho square. So this quantity, this plus this is a function of rho alone, whereas phi double dash phi by phi phi is a function of phi alone. So a function of rho is equal to a function of phi. That can happen only when both sides are constants. That means you must put phi double dash of phi by phi phi, you must call this as minus some constant m square, and here you will get rho, here you get rho square r double dash of rho plus rho r dash of rho plus rho r dash of rho plus H square rho square plus H square rho square minus m square r of rho is 0. So you will they will satisfy two different equations, and this is a harmonic oscillator equation. You know that the solution can be written as a linear combination of cos m phi and sin m phi, and m must be necessarily an integer because otherwise it won't be single valued. So m must be an integer. You can say m is either 0, 1, 2 or so on, and the solution to this is a Bessel equation of order m with the replacement that with the after making the change of variables h rho equal to x. So, this has got a solution, R has got a solution, R rho will be equal to C1 times Jm of h rho plus C2 times Ym of h rho, where Jm is the Bessel function of order m and Ym is the modified Bessel function of order m. Since we require the fields to be non-singular, they should not blow up, there should not be any singularity in the fields. When rho becomes 0, you must delete this choice, because the second modified Bessel function has a singularity at rho equal to 0. So, R rho becomes simply proportional to Jm h rho, and you can write the entire mode as R rho phi phi, you can write as being proportional to, say you can write it as a linear combination of cos m phi, C1 cos m phi plus C2 sin m phi multiplied by Jm h rho. Here h is as usual gamma square plus omega square epsilon mu, where gamma, the dependence on z is e power minus gamma z, so that dou square by dou z square becomes gamma square. And if you apply the boundary condition in the Dirichlet case, suppose you are looking at first the transverse magnetic mode, that means Hz is 0, so everything is derived from Ez. So, you have that Ez at rho equal to R, this must be 0, that amounts to saying that Jm of Hr must be 0. That means Hr must be one of the roots of the Bessel function Jm. I denote the roots of the Bessel function Jm by xn, or let us call it as alpha n. So, Jm at alpha mn. Alpha mn are the roots of the Bessel function of order m equal to 0. So, alpha m are these roots, alpha m n takes the values 1, 2 and so on. So, I can write hr as alpha mn, or equivalently h is equal to alpha mn by r. Likewise, if you have the Neumann condition, instead of the transverse magnetic mode, if you take transverse electric mode, then Ez is 0, then all the fields are derived from Hz, and Hz will be equal to C1 cos m phi plus C2 sin m phi multiplied by Jm h rho, with the only difference that now dou Hz by dou rho should vanish at the boundary, which amounts to saying that Jm dash at h rho should vanish when rho is r. So, this should be r. So, if I denote the zeros of the derivative of the Bessel function of order m by, if you denote these zeros by beta mn, n equals 1, 2 and so on, then you get that h is equal to beta mn divided by r. So, what is the final solution? You first switch off the Hz component, so that it becomes a transverse magnetic, calculate the solutions to the fields. Then you switch off the electric field and calculate the magnetic field, and then you superpose both the solutions, because Maxwell's equations are linear. That is the complete most general solution for the fields within the cylindrical waveguide. So, what you get is that Ez of rho phi z at a given frequency can be written as summation Cm cos m phi plus Dm sin m phi with Jm of alpha mn. Ez should vanish on the boundary, right. So, alpha mn rho by r, where alpha mn are the roots of Jmx equal to 0, and you are going to sum this over all mn n, and you will also put a factor of e power minus gamma mn z, where what is gamma mn? Gamma mn square is determined by gamma mn square plus omega square epsilon mu equals hmn square. In this case, your h is alpha mn by r, right. We had written the solution as Jm h rho, and when you applied the boundary condition, you put hr equals alpha mn, so that the Bessel function vanishes on the boundary, which is equivalent to saying h is alpha mn by r. So, this is alpha mn square by r square, or equivalently gamma mn square, gamma mn is equal to alpha mn square by r square minus omega square epsilon mu power half, and obviously it will propagate. This is the equation for the TMM mode. TMM or transverse magnetic, where Ez is not 0 whereas Hz is 0, and this will propagate when omega square epsilon mu is greater than alpha mn square by r square. So the cutoff frequency is omega c mn, the cutoff frequency for the mth mode, mth transverse magnetic mode. The cutoff frequency for the mth transverse magnetic mode is given simply by the equation omega c mn is equal to alpha mn by r root epsilon mu. This should be greater than this, so that gamma mn becomes pure imaginary, it propagates without any attenuation. So you get the complete solution to the transverse magnetic mode. Likewise, for the transverse electric mode, you will get Hz of rho z phi, rho phi and z will be of the form some Cm cos m phi plus Dm sin m phi multiplied by Jm of beta mn by r into rho summed over mn. This is the transverse electric mode. Once you know Ez and Hz, you can derive the transverse components by going back to the formula E perpendicular and H perpendicular is equal to minus gamma by H square del perpendicular, and here also del perpendicular, you can get back the complete solutions. Okay, so that solves the problem of calculating the modes within a cylindrical waveguide. What about a cylindrical cavity resonator? In a cylindrical cavity resonator, you close the top surface and the bottom surface by lids, right? You close this Z equal to D here, and this is Z equal to 0. So Hz vanishes on the boundary. Hz vanishes, Hz is 0 when Z is 0 or D. Likewise, E rho and E phi, the tangential components of E also vanish on the perfect conducting surfaces, which are the top lids and the top, which is the top lid and the bottom lid. So this is also 0 when Z is either 0 or D. So if you apply this condition, what do you get? Let us take the transverse electric case first. So everything is derived from Hz. So you are going to write the dependence on Z is e power minus gamma mn z, but you could write it as plus minus gamma n. So if you choose the correct linear combination which vanishes on Z equal to 0 and D, it will be obviously that gamma mn must be of the form j beta mn, where, and you should choose the combination e power gamma mn z minus e power minus gamma mn z. This will vanish at Z equal to 0 and Z equal to D, provided if you put this will also of course proportional to sin h gamma mn z, and since I have put gamma mn equal to j beta mn, this is proportional to sin of beta mn z. So this will vanish at Z equal to 0, and at Z equal to D it will vanish when beta mn is of the form beta mn d is of the form p pi by where p is some integer, or equivalently beta mn is of the form p pi by d, right. So you get, and once you put beta mn is equal to p pi by d, you get the value of gamma mn as j p pi by d. And so if you look at the characteristic frequencies, they are determined by omega square epsilon mu plus gamma mn square, which means minus p square pi square by d square. You are talking about the transverse electric case. In the transverse electric case, everything is derived from the magnetic field. So the roots were beta mn, hmn square. Hmn square was nothing but beta mn square by r square, where beta mn were the roots of the derivative of the Bessel function. So the possible frequencies of oscillation are m and p for a transverse electric mode. The possible frequencies of oscillation within the waveguide, within the resonator cavity, are 1 by root epsilon mu multiplied by beta mn square, beta m n square by r square plus p square pi square by d square power half. Likewise, in the case of an electric transverse magnetic mode, in the case of the transverse magnetic mode, everything is determined by Ez, and you require that Ex, E rho and E phi should vanish, that is E perpendicular, the transverse component of the electric field should vanish when Z is equal to 0 and D. But what is the transverse electric component in the Tm case? it is minus gamma by h square del perpendicular to Ez. So, if del perpendicular Ez is to vanish, what is gamma? Gamma has to be replaced by dou z minus dou z. So, this can also be written as, because plus or minus gamma you can admit, you can replace gamma by minus gamma, that will also be a solution. So, in general you should write this expression as 1 by h square del perpendicular dou Ez by dou z, dou Ez by dou z. So, so dou Ez by dou z should vanish, dou Ez by dou z, dou Ez by dou z should vanish when z is 0 or d. That is because del perpendicular, this will automatically vanish when z is 0 or d, because del perpendicular involves transverse derivatives with respect to x and y. So, if something is some function of z vanish, some function of x and y vanishes on this boundary, then its derivative with respect to x and y will always also vanish on the boundary, because as x and y vary, it moves only on the top boundary. If some function of f of x y is 0 here, then dou f by dou x, dou f by dou y, they will all be 0, right, because it is 0 for all x y falling on the surface. So, in the case of the transverse magnetic mode, you had the solution cos m phi, sin m phi, linear combination, and here you put Jm. Transverse magnetic means you have the Dirichlet boundary conditions. So, alpha mn rho by r into e power minus gamma mn z is to be replaced by sine of pi p by z. But you require dou Ez by dou z to vanish. So, you should put cos, you should put cos of p pi by z, because its derivative with respect to z, cos pi p pi z by d. Let me write it clearly. In the case of the transverse magnetic mode, where Ez is given by summation over m Cm cos m phi plus dm sin m phi multiplied by Jm of alpha mn rho by r. You will not put e power minus, you are taking that particular linear combination, so that dou Ez by dou z vanishes at the bottom plane as well as at the top plane. So, you put here sine, you put cos of p pi z by d, cos of p pi z by d, and anything else. So, cos p pi z by d where p is any integer, right, where p is any integer. And also you have to put a time function exponential j omega. So, for the transverse mode, transverse magnetic mode, you write it as omega e mnp t, and you put a real part where Cm and dm can be complex numbers. So, you put a real part here, where your omega e mnp are the possible modes of oscillation, namely omega e m n p are given by 1 by root epsilon mu times alpha mn square by r square plus p pi square by d square power half. These are the possible frequencies of oscillation within a resonator when you consider the Tm mode. Likewise, for the Te mode, what happens? For Te mode, everything is derived from Hz, and the boundary condition which you apply here are that Hz should vanish on the top and bottom. So, this will give you a sine term. The dependence on z will be sin p pi z by d, sin p pi z by d. So, the complete solution for Hz is given by, here it will be as a function of t, rho, phi and z. This will be equal to summation over all m Cm cos m phi plus dm sin m phi, sin m phi multiplied by Jm. Since you are using Hz, the boundary condition on Hz is that dou Hz by dou rho should vanish on the at rho equal to r. So, this will be Jm of beta mn rho by r multiplied by e power j omega So, here you will put this is a transverse magnetic electric mode omega MNP t, then you put a real part of this where Cm and Dm can be complex numbers, and your omega MNP is nothing but 1 by root epsilon mu, the possible mode frequencies of oscillation. Here you will put beta Mn square by r square plus p square pi square by d square power half. P is an integer, beta Mn are the roots of the derivative of the Bessel function. Jm dash of beta Mn is 0, whereas in the case of the transverse magnetic modes you had Jm dash of alpha Mn equal to 0, alpha not Jm dash, here you had Jm of alpha Mn equal to 0, that is alpha Mn were the roots of the Bessel functions, whereas beta Mns were the roots of the derivative of the Bessel function. That completely solves the cylindrical problem. Now let us look at the case when you have a cavity resonator, when you have a cavity resonator with an atom inside like this. So this is an atom with an electron around it, atom with an electron. How do you model this system? So you say that the atom is located at the point r0 within the waveguide, and the fields are E and H as a function of t x y z or t rho phi and z, and you want to look at the transitions induced by the fields in this atom when it makes a transition from one state to the other caused by the electromagnetic radiation falling on it. So from E and H, first you derive an expression for the scalar potential phi and the vector potential A, that is the first step. So how do you derive it? You have to say minus del phi at a given frequency minus j omega A equals E, and similarly del cross A is equal to del cross A by mu equal to H. You solve these two equations. One way to solve this is, since there are no charges inside, you can assume phi as 0, and you can simply say A equals minus E by j omega. You can adopt a proper gauge. You can adopt a gauge in which is called the Coulomb gauge, in which phi is 0. The Coulomb gauge phi is 0 and divergence of A is 0. Okay, there are no charges. So divergence of A is 0 and this. So you get immediately the value of E. If you substitute the value of E into this equation, you will see that it is fully consistent, because if you substitute A into this expression, you get minus 1 by j omega mu into del cross E equal to H, or equally del cross E is equal to minus j omega mu H, which is Faraday's law of induction in the frequency domain. So it is consistent. So you get A and phi. Now you look at the Hamiltonian of the atom. It is P plus Ea square by 2m minus E phi. This is the Hamiltonian of the atom. So it can be written as, since it is located at r0, your P is nothing but minus del minus I h cross del at that point. Let us say del with respect to some xi. That means the nucleus is at r0, whereas the electron is at r0 plus xi. The displacement of the electron relative to the nucleus is xi. So you put del xi here plus E times A. Now A is evaluated at time t at the point r0 plus xi at the site of the electron, and you put the square of this here divided by 2m minus E times phi at t r0 plus xi. So this becomes the Hamiltonian. This is a Schrodinger Hamiltonian. If you use the Dirac Hamiltonian, then you have to take into account the gamma matrices or the alpha matrices of anti-commuting alpha matrices of Dirac, and then calculate this. So now we apply perturbation, time dependent perturbation theory to this to calculate the transitions. So let us see how to do it. You start with the Hamiltonian H equals minus I H del xi plus Ea square minus E phi. So you expand this is equal to by 2m, this is minus h square by 2m into del xi square minus I h E by 2m into del xi dot A. That means you put divergence of A with respect to xi. See, when you expand this operator, when you take two operators, say A and B, and you square them, what do you get? You get A square plus B square plus AB plus BA. And you cannot write them as, you cannot write it as 2AB. When you multiply them, you will get both the orders in the coming into the picture. So here this will be del xi dot A acting on a wave function. When you square this and apply this on a wave function psi, you will get del xi dot A psi plus A dot del xi psi, which is nothing but 2A dot del xi psi plus divergence of A with respect to xi multiplied by psi. So this will be div xi A plus div xi A plus 2 A dot del xi, A dot del xi. That's what you will get, and this plus an E square plus E square A square by 2m plus E square A square by 2m minus E phi. So you get the Hamiltonian as the sum of, you can of course add to this the interaction between electrostatic potential energy interaction, the interaction of the electron with the nucleus through its electrostatic potential energy, that is through the Coulomb interaction of the electron with the nucleus. So you can write that as minus Ze square by R by xi, Ze square by mod xi. So in effect I can write the entire Hamiltonian of the atom, of the electron interacting with the radiation field, as the unperturbed Hamiltonian of the atom plus E times 1 potential V1T. So you can write down the interaction energy of the electron with the nucleus and with the electromagnetic field, which is present within the cavity resonator in this form. So your HT is what? You have HT is minus I H cross del xi plus EA square by 2m minus E phi. If you expand this, you will get these two terms, where your V1T is an operator which is defined by minus IH E minus IH by 2m minus IH by 2m. You expand this square, this becomes div xi A plus 2A dot del xi and minus phi. So this interaction energy is an operator, this is a multiplication operator, this is a difference, this is a vector field, a differentiation operator with respect to phi, and these have to be evaluated at time t and at the point r plus xi of the electron. And what about V2T? V2T is the order E square. I am expanding the Hamiltonian in powers of the electronic charge, because electronic charge is a convenient perturbation parameter. So V2T is nothing but A square by 2m, A square by 2m. So now we can apply perturbation theory to this, time dependent perturbation theory. Perturbation theory. If you apply it, you get the wave function of the electron at any time as d by dt of psi t is equal to h0 plus E V1t plus E square V2t multiplied by psi t. This is Schrodinger's equation for the wave function. You expand the wave function in powers of the electronic charge. So this becomes psi t0 plus E times psi t1 plus E square psi t2 plus so on. You substitute this into this equation and equate equal powers of the electronic charge on both sides. So if you equate order e power 0 term, what do you get? You get IH cross, say H cross, IH cross d by dt of psi t0. This is nothing but the unperturbed atomic Hamiltonian. Remember, the unperturbed atomic Hamiltonian is simply minus h square by 2m del xi square minus Ze square by r, where this is the Coulomb potential, Coulomb interaction potential between the nucleus and the electron, and this is the kinetic energy operator of the electron. So this is h0 multiplied by psi t0. Then IH cross d by dt of psi t1 is order E term, which is h0 multiplied by psi t1 plus V1t multiplied by psi t0. Let us go up to order 2 plus IH cross, this is order E term. The order E square term is IH cross d by dt of psi t2. This is h0 multiplied by psi t2 multiplied by psi t2 plus V1t multiplied by psi t1 plus V2t multiplied by psi t0. Psi t0. So, we solve these equations using standard methods in differential equations. You get that psi t0 is equal to u0t acting on the initial state. Let us say the initial state is the state n, the stationary state n of the atom, okay, and u0t is the evolution operator in the absence of any perturbation, e power minus I t h0 by h cross, evolution operator of the electron in the absence of any perturbations, any external perturbations. What about psi t1? Psi t1 satisfied the equation d by dt of psi t1 is equal to minus I by h cross h0 acting on psi t1 minus I by h cross into V1t multiplied by psi t0. So, the solution here is psi t1 is equal to, you are starting with psi, the initial perturbation is 0. So, it will be simply a convolution minus I by h cross integral e power minus I t minus tau. So, u naught t minus tau into V1 tau into psi tau 0 d tau from 0 to t. You can substitute for psi tau 0 from this equation and you get that psi t1 equals minus I by h cross integral u0 t minus tau into V1 tau into psi tau 0. So, that was nothing but u naught of tau multiplied by n d tau from 0 to t, where u naught t is the unperturbed evolution operator. Similarly, what was the equation for psi t2? The equation for psi t2 was d by dt of psi t2 is equal to minus I by h cross h0 acting on psi t2 minus I by h cross V1t acting on psi t1 minus I by h cross V2t acting on psi t0. So, you can again solve this by the usual convolution method for solving first order differential equations. The initial perturbation as 0. So, this is nothing but minus I by h cross integral from 0 to t u naught t minus tau into V1 tau times psi tau 1 plus V2 tau times psi tau 0 d tau. You can substitute for psi tau 1 from this equation. You can substitute. Let us look at just the first order perturbation and see how to calculate transition probabilities using that. So, you neglect order E square to start with and say that psi t1, the electronic wave function, is approximated by psi t0 plus E psi t1 plus order E square. So, psi t1 is nothing but minus I by h cross integral from 0 to t u0 t minus tau into V1 tau into u0 tau multiplied by n d tau. So, after time t, what is the transition probability? The wave function is this. After, what is the transition probability amplitude? The probability amplitude of the electron making a transition to another stationary state m after the perturbation has been switched on. It is psi t0 plus E psi t1. But you see, psi t0 is orthogonal to m because these two states are distinct. Because psi t0 is simply ut acting on n, right? What is psi t0? Psi t0 is nothing but u0t acting on n. So, if this stationary state has an energy En, this is e power minus I En t by h cross into n, and n is orthogonal to m because they are two different stationary states. So, this will not contribute anything. So, this will be simply electronic charge times this transition probability amplitude, and you can calculate that very easily from this. So, you see that you can say that transition probability, the probability of it is making a transition in time t from n to m is equal to simply m into psi t square approximately up to order E, which is equal to E square times E square by h square times magnitude of integral from 0 to t, then m you have here you have u0 t minus tau v1 tau, and then you have u0 tau n d tau mod square. u0 tau is e power I n minus I n tau. So, this can be written as E square by h square times mod of integral from 0 to t, then here you have e power I e n tau by h cross, and here you have e power u0 t is acting in the as an adjoint conjugate of this. That is, if you look at this ket vector, this bra vector multiplied by ut, this is nothing but u0 t star. u0 t star is same as u0 t, okay, u0 star is same as u0 t inverse because the unitary operator. So, m, then you put a star here. So, this is nothing but e power I m t by h cross I m e n sorry, this is e power I e m t by h cross times m star, which is nothing but m e power minus I e m t by h cross. So, here you will get e power minus I e m t minus tau by h cross multiplied by the matrix element of the perturbing potential. This is also called Fermi's golden rule. So, d tau square. So, in effect you are taking the Fourier transform of the matrix element of the interaction potential energy. You can write it as, you can write this same thing as E square by h square times magnitude of integral from 0 to t. Now, this is a e power minus I m t, this will come out as a factor whose modulus is 1, it will come out of the integral. So, it can be written as simply m v1 tau n multiplied by e power I e n minus e m, e power I e n minus e m tau by h cross d tau square. This is Fermi's golden rule, which says that the transition probability up to order E square is equal to the Fourier transform of the matrix element of the potential energy evaluated at the Bohr frequency, and the Bohr frequency is the transition frequency between the states E n and E m. It starts with the state, it starts in the state n, and it goes to the state m. So, you can write this as E m minus E n is the Bohr frequency, this is omega m n, and this can be written as e power minus I omega m n. So, transition probability in going from the state n to the state m in time t is equal to E square by h square times mod integral from 0 to t, then you go from the state n to the state m. So, v1 tau n e power minus I omega m n t tau d tau square. It is the Fourier transform of the matrix element of the interaction potential energy, between the field and the atom. You can compute it to order 2 also, the same thing. The whole point is that your v1 tau is given by v1 t here is given by the following expression. It is minus IH by m into div xi a plus 2a dot del xi minus phi, and these a and phi depend on the waveguide fields or the resonator cavity fields, which in turn depend on the dimensions of the waveguide. So, by measuring these transition probabilities, you get information about the dimensions of the waveguide or the dimensions of the resonator, and you can estimate these parameters very easily. Now, you can ask a more difficult question: what happens when you quantize the field within? How do you quantize? How is the EM field within the waveguide, within the cavity quantized? How is it quantized? We have already discussed this problem in an earlier lecture, in which we quantized not only the electromagnetic field but the Dirac field also, and then the two interact with each other, and then there is a noisy bath around. So, you have a situation in which you have a cavity resonator like this, here you have a noisy bath, okay, which is modeled in the Hudson-Parthasarathi formalism in terms of creation, annihilation and conservation processes. the noise processes of quantum stochastic calculus. Noise processes of quantum stochastic calculus. So, you want to model it and calculate the transition probabilities. Let us use the Dirac equation this time to do the quantization. So, first you consider just the electromagnetic field within the cavity and you quantize it. You can write the fields as, you can write the vector potential A of T and R in terms of the modes, within the cavity. So, these modes are nothing but the coefficients which appear in the expansion of the electric field and magnetic field, Cn and Dm, they become operators. So, this magnetic vector potential you can write as summation some An. I am denoting all the three indices M and P by a single integer n. So, An into some basis functions Un of R, Un of T and R plus An dagger Un of T R bar summed over n. If you calculate the total energy, likewise you can do for the since you are choosing a gauge in which phi is 0, you do not bother about the electric scalar potential. If you compute the total energy of the field, what is the energy of the field within the cavity? It is a quadratic form in An and An dagger. You can see that this energy must be of the form summation omega n An dagger An, where omega n's are the characteristic frequencies of oscillation within the cavity. Because when you, how do you calculate the energy in terms of the vector potential? The energy is given by half E square plus half h square dV over the volume of the cavity, and this can be written as half dou A by dou T, square plus half del cross A square dV over the cavity, and del cross A square can be written as if you look at the expansion for the for A, if you write it in the Fourier domain, what happens? Or if you write it in terms of the coefficients, what happens? You are writing A as summation An into Un RT, Un TR plus An dagger Un TR bar. These are of course vector valued functions. They are coming from the modal expansion. That is, if you calculate all the three components of the electric field and all the three components of the magnetic field, you will get a vector modal function Un TR. And if you substitute this into the equation, say dou A by dou T, you try to calculate dou A by dou T square dV over the cavity. If you calculate, then you will get a quadratic form in An and An dagger. Likewise, if you calculate curl of A square dV over the cavity, you will get another quadratic form in An dagger, and if you add the two, you will get the Hamiltonian of a harmonic oscillator, of a sequence of independent harmonic oscillators oscillating at the characteristic frequencies. If you use the orthogonality of the modes, the cross terms will cancel out. For example, you can see that dou Un by dou T will come, this will give one of the terms, and then you calculate dou Um by dou T, this will give another mode, and when you take the integral of this will be 0 when n is not equal to m, because dou Un by dou T will be the frequency times Un, dou Um by dou T will be the frequency times Um, and then when you take the orthogonality, when you consider the orthogonality of the modes, the cross terms will cancel. So, you will get, similarly for curl A square, how do you calculate curl of A square? Curl of A square is nothing but del cross A dot del cross A, okay, dot product dV. Now, if you write it as del dot, so this can be written as del cross A dot B, because del cross A is B dV. Now, if you look at del dot A cross B, del dot A cross B can be written as del cross A dot B minus A dot del cross B. So, del dot A cross B integral is 0 by the Gauss divergence theorem. Del dot A cross B dV over the cavity is simply equal to A cross B dot n ds, where n is the normal to the cavity, and by the boundary conditions on the boundary, this A and B will cancel out. So, you will get only if this is the cavity, then this is the boundary of the cavity, it is integrated over the boundary. So this integral will go away, you will get del cross A dot B is equal to A dot del cross B, right. So integral of del cross A dot B dV will be the same as integral A dot del cross B, which is nothing but integral A dot del cross A. But divergence of A is 0 because we have chosen the Coulomb gauge. So this will be minus integral A del square A. So and del square A satisfies Helmholtz equation. Okay, what does A satisfy? It satisfies del square plus each mode will satisfy the Helmholtz equation. So it will satisfy del square plus omega n square, where omega n is the characteristic frequency of oscillation, multiplied by an. If an is the nth mode, that is 0. So this will be a sum of the modes minus summation an minus summation of an square into omega n square by c square. So you can see that you will get a quadratic form in the creation and annihilation operators. That means the entire Hamiltonian of the electromagnetic field within the cavity can be written as a superposition of these modes, omega n, an dagger an, summed over all the n's. And you can see that these an's will satisfy the canonical commutation relations as follows from when you quantize the fields. You see, when you write down the Hamiltonian, when you write down the Lagrangian, as half dou A by dou T square minus del cross A square dV. You write down the Lagrangian of the field within the cavity in this form. Then what is the canonical momentum? If you take A as the canonical position fields, then what are the canonical momentum fields? They are pi tr given by dou L by dou A by dou T, which is equal to dou A by dou T. So you get a canonical commutation relation which says that A of tr comma dou A by dou T at t r dash, and if you take the ith component and the jth component, then this is equal to delta ij, it's actually the I h cross times delta ij into delta 3 r minus r dash. These are the canonical commutation relations. If you translate this canonical commutation relations to commutation relations for the coefficients an and an dagger, using the fact that if un is an orthonormal set of functions, then un r dash bar summed over all the n, this is delta 3 r minus r dash. If you use this identity for orthonormal functions, for an orthonormal basis of functions of L2 of the cavity, un is an orthonormal basis of L2 for L2 of the cavity, L2 of the volume within the cavity with respect to the Lebesgue measure. So if you use this, you will get simply that the Hamiltonian that, and if you translate the commutation relations, canonical commutation relations between A and within the position fields A and the canonical momenta A equal time commutation relations, you will get a commutation relations for the an which say that an comma am dagger is equal to delta nm, and an comma am, this is 0, and an dagger comma am dagger, that is also 0. So you are able to represent the entire electromagnetic field within the cavity as a sequence of harmonic oscillators, independent harmonic oscillators. So the field Hamiltonian becomes simply electromagnetic field Hamiltonian becomes simply summation omega n an dagger an, where these are characteristic frequencies of the oscillation omega n, and these are the creation of annihilation operators an and the creation operators an dagger. Now you consider this electromagnetic field interacting with the bath outside. So the bath outside is described by the quantum noise processes of Hudson and Parthasarathi. Hudson-Parthasarathi quantum stochastic calculus. It is based on this formalism. Hudson-Parthasarathi quantum stochastic calculus. This calculus was developed with the aim of showing that of giving a rigorous basis for noisy quantum systems in terms of non-commutative noise. so that when you write down the evolution equation for observables and for density matrices of the system and bath, and you take the trace over the bath variable, so that you get an evolution equation for the system state alone, that will be the Sudarshan-Lindblad equation, Gorini-Kosakowski-Sudarshan-Lindblad equation, GKSL equation, or the master equation in quantum mechanics for noisy open quantum system, master equation for open quantum systems, for open quantum systems. So this is a modification, a generalization of Schrodinger's equation, or the Schrodinger-von Neumann-Liouville equation in quantum mechanics when there is noise present, and you do not describe the evolution of the wave function, you describe the evolution of the density matrix. So this evolution equation states that d rho by dou t can be written as the sum of a Schrodinger part minus I h comma rho, where h is the Hamiltonian, minus half times in terms of Lindblad operators Lk dagger Lk rho plus rho Lk dagger Lk minus 2 Lk rho Lk dagger. So this is a linear equation in rho, where rho is now a density matrix, and this can be obtained by considering a Hamiltonian equation of the form a random Hamiltonian. You can consider a random Hamiltonian ht comma rho t, ht comma rho t. So the rate of change of the density is given by minus I ht comma rho t. So rho at t plus tau, if at t, tau is very small, is approximately rho of t minus I times integral from t to t plus tau hs comma rho s ds, and this can be further approximated as minus rho t minus I. You substitute for rho t within this. So this is integral from t to t plus s, t plus tau, and this is hs. Now wherever rho s comes, you again substitute the same expression inside. So you will get hs comma rho s. Just try to write this down in that form. So it will be hs comma hs prime comma rho s prime ds prime. Okay. Of course there will be an h0 term also. Just try to write this. You see, how do you derive the master equation in quantum mechanics? How do you derive the master equation in quantum mechanics? You start with the normal Schrodinger equation for the density, for the mixed state. You write it as ht comma rho t. Then you look at rho at t plus tau. Rho at t plus tau can be written as rho of t minus I times integral from t to t plus tau hs comma rho s ds. So this can be written as rho at t minus I times, now wherever rho s comes, you use this the same equation again. So it can be written as minus I integral from t to t plus tau hs, then rho s can be written as rho t minus I by h cross. Let us say h cross is 1 here. So minus I times here you are having rho t plus I, here you will have approximately it will be ht comma rho s, because s is close to t, and then you get ds ht comma rho ht comma rho s prime, and then ds prime. So here you are integrating with respect to s, and here you are integrating with respect to s prime. So you get rho of t plus tau is approximately equal to rho of t minus I times integral from t to t plus tau, t to t plus tau hs comma rho t, which can be replaced by ht comma rho t. So this can be replaced with minus I ht comma rho t into tau, and this becomes a second order term. So this will become minus ht comma rho t, and you have a double integral ds prime, so that will give you tau square. Now if you assume that ht has a white noise component, and you take the average over all this, you will get the open the master equation of quantum mechanics. If you take the average on both sides, this term is the usual Hamiltonian term. This term will give you a term of the form ht, ht, rho t. We are taking an average over all ensembles of ht. Ht is a random Hamiltonian. Ht is a random Hamiltonian. So this will be nothing but h square ht square rho t plus rho t into ht square minus 2 ht rho t rho t into ht, and then you take the average. You write ht as a linear combination of Lindblad operators with random parameters and take the average, then you will get the master equation. This is only a heuristic derivation of what happens when a system interacts with a bath with randomness coming from the bath. But Hudson and Parthasarathi gave a very rigorous formulation of this equation. They said that we shall treat the bath as a boson-Fock space consisting of an indefinite number of bosons interacting with the system, so that the total Hilbert space of the system and bath is described by a tensor product of the form gamma sh. So the noise processes live in this space, whereas the system variables live in this space. And you can develop a quantum stochastic calculus of creation, annihilation and conservation operators in such a way that you can define a quantum Brownian motion on the boson-Fock space, with the quantum Brownian motion satisfying a quantum Ito formula, namely an equation of the form dAt dagger equal to dt, equal to h cross dt, ideally speaking. In normal Ito stochastic calculus, you have dBt square equal to dt. So this equation is not derived using any statistics, it is derived using purely functional analytic methods. It is based on using the indicator functions as corresponding to an increasing family of spectral projections which defines the time evolution operator. And this is a consequence of Heisenberg's uncertainty principle, non-commutativity of the observables. So Ito's calculus comes in the avatar of Heisenberg's uncertainty principle. Heisenberg's uncertainty principle leads to naturally to Ito's formula for Brownian motion. We shall see that later on. So if you write down the unitary evolution of the system and bath, the joint state of the system and bath using these processes, and then you trace out over the bath variables, then naturally you get a Sudarshan-Lindblad equation, a master equation for the system state. So we shall see a little bit of this derivation later on. And I'll just focus on how we apply this to the Dirac equation. So the Hudson-Parthasarathi equation is dUt is equal to minus I h plus LL dagger by 2 dt plus, let us say, just you have one Lindblad operator, L dat minus L dagger dat dagger acting on ut. This is a quantum Ito correction term where dat dagger is dt. This quantum Ito's formula is a very curious thing, you see. You have dat dagger, if you take h as 1, this is dt, whereas dat dagger dat is 0. That is the order, it is of order smaller than dt, this is 0. And likewise dat square is 0 and dat dagger square, these are all 0. It's all 0. How does one derive this equation? You start with things like, say, an annihilation field and a creation field which satisfy the canonical commutation relations, namely u comma v, and you replace u by an indicator function. So u is replaced by some some m times some mt, which is of the form which is m, which can be written as m times chi 0 t, where chi 0 t is the indicator of the interval 0 to t and m is a function in L2R. So in place of u, you get then a, in place of this relation you get chi 0 t comma a of m chi 0 t dagger. Here you, instead of v, you put 0s here, so it becomes 0s, and this is nothing but the inner product between these two. So here you put m1, here you put m2. So this becomes the inner product between m1 and m2 over the time interval 0 to minimum of t and s. So it is this fact which gives rise to the quantum Ito formula, if you define your if you define ATM to be equal to A m chi 0 t, where m is a fixed vector in the L2R, then automatically this equation, if you take differentials with respect to t and s, gives rise to Ito's formula. That will be seen by differentiating with respect to t, taking the differential on this side with respect to t, on both sides first with respect to t and then with respect to s, right. So if you have an equation of the form, say AT of m into AS of m, you put m1 and m2 here, this is equal to the inner product between m1 and m2 taken over the interval 0 to minimum of t and s, which is nothing but integral m1 m2 du from 0 to t, minimum of t and s. If you take the derivative on both sides with respect to t first, what happens? You get dAt, here it should be dagger, dAt of m1 comma as of m2 dagger. So if you take the differential with respect to this is some function of t and s, the minimum of t and s. So you can write this function of t and s as the minimum of t and s as fs if t is greater than s. So you put a heaviside step function here, t minus s, or it is ft if s is greater than t. So if you take the differential with respect to t on both sides, you get something like this, right? dAt by dt formally is equal to, if you differentiate this, you get fs into delta of t minus s. If you differentiate this with respect to t, you get plus f dash of t into theta s minus t. Here you differentiate minus f of s into delta s minus t. So fs in ft minus fs into delta t minus s minus fs into delta s minus t, that will cancel out. Again, if you differentiate with respect to s this equation, you get f dash t into delta t minus s and into delta t minus s. So if you f dash t into delta plus f double dash of s, that term will cancel out. If you use the formula integral from 0 to t m1 m2 du is equal to f of t, and f dash t gets replaced by m1 m2. So that will immediately lead to quantum Ito's formula, right. So you will get dAt at m1 multiplied by dAt at m2 dagger. This is nothing but m1t, m2t, m1t bar, m2t dt, the general form. So this is called quantum Ito's formula. Quantum Ito's formula is a natural consequence of the Heisenberg uncertainty principle, because it has been derived using only the commutation relations between operators. You see, Heisenberg's uncertainty principle is that states that if two observables don't commute with each other, then they are not simultaneously measurable. That means you cannot assign a joint probability distribution for these two observables in any state. That is, no matter how, if two observables don't commute, say A and B don't commute, then A comma B is not 0. Then what will happen is, if you take the variance of A in a given state and you take the variance of B in the same state, B square in the same state, then by using the Cauchy-Schwarz inequality, this can be written as A psi comma A psi multiplied by B psi comma B psi, which is greater than or equal to A psi comma B psi mod square, which is greater than or equal to the imaginary part of A psi comma B psi, which is nothing but imaginary part of A psi comma B psi square, which is nothing but 1 by 4 times A psi comma B psi imaginary part is A psi comma B psi minus the conjugate of that, which is B psi comma A psi. So you can bring the A to this side and write it as psi comma A comma B psi square. So when A and B don't commute, this will be no longer 0. So, the product of the variances of A and B in any state is always greater than 0. That is the Heisenberg uncertainty principle. So, naturally from non-commutativity the uncertainty principle arises, and since the quantum Ito formula of Hudson and Parthasarathy has been derived using only non-commutativity of the creation and annihilation operators, we can view the quantum Ito's formula which results from that as a direct consequence of the Heisenberg uncertainty principle. Next time I shall discuss how the Hudson-Parthasarathy equation for a noisy quantum system or a quantum system interacting with a bath can be used to formulate the dynamics of the electromagnetic field within a cavity resonator in the presence of bath noise. Then we shall consider the fermionic noise case also, where the field within the cavity consists of not just the electromagnetic field but also a Dirac field of electrons and positrons, which are described in terms of second quantized wave functions, and that interacts with the electron positron field and the photon field outside. So, instead of creation and annihilation operators for bosonic processes, we will also have fermionic creation and annihilation operators satisfying the canonical anti-commutation relations, and we can derive the fermionic anti-commutation relations from bosonic commutation relations using a famous theory due to Hudson and Parthasarathy. Then we shall look at the filtering problem for these fields. That is, Belyavkin developed a quantum filter for filtering out noisy observables which evolve according to the Hudson-Parthasarathy theory by using non-demolition measurements. Non-demolition measurements mean that these measurements commute with the future value of the state as well as among themselves. So, you can define a joint probability distribution of a future value of the evolving or Heisenberg observable and the measurement processes, as well as a joint probability density of the measurement processes, joint probability distribution of the measurement processes, because they are non-demolition, they commute with each other. Whenever they commute, the Heisenberg uncertainty principle does not apply, they are simultaneously measurable. You can assign a joint probability distribution for the observables in any given state when the observables all commute with each other, because they can simultaneously be diagonalized. So, we shall look at how Belyavkin developed a filter based on this, and he showed that this turned out to be a generalization, a quantum mechanical non-commutative generalization of the famous Kushner-Kalyanpur filter, Kushner-Kalyanpur classical stochastic nonlinear filter. You can derive the Kushner-Kalyanpur filter from this, and you can derive more. The corrections to the Kushner-Kalyanpur filter, when you use the Belyavkin filter, you will get corrections of the order of Planck's constant and higher powers in H cross. So, we shall see how these extra corrections enter into the picture, and then describe a cogent filtering theory for how to calculate, how to estimate the quantum electromagnetic field within a cavity from non-demolition measurements when there is a bath surrounding it, with the bath consisting of electrons, positrons and photons. So, I shall stop at this point.